Today we are going to try and write this contest. I hope we succeed. So the contest will be a good one. Excellent. So we do not want to rotate these blocks. We want to make a square using these blocks. I think it's quite easy. Yes, this problem should be quite easy. I don't see any reason for it to be not very easy. So we just read T, read N. What next? Oh, it's so noisy. Ah, everything is rounded up. Hmm. You know what? Everything is rounded up. So it's like, uh, for example, if we have an even n, then we have n halved, then 2 times n minus 1, this minus 1, this. Ah, no, it's like this. I guess it's just n halved. And in the other case, when we have 2 is not divisible by n, yes, it should be just. Hmm. What about this case? So we have 4, 4, 3, 1, and 3, 1. But can we do like this? I guess we cannot do it. So it's just always and half rounded up. Let's try and do it. One, 3, 9, and 8. Okay. Some people already solved problem B. An empty string is diverse if the number of occurrences of each character in it doesn't exceed the number of distinct characters in it. Okay. Find how many of its strings are diverse. I think it's some sort of um, hmm. This means that we only need to look at the strings of length at most 100. Okay, so it seems obvious. So we have if this number equals 1, then plus plus ds, and always a max equals max of a max and this number. And if ds is greater than a max, okay, no, if ds is, yeah, if it is at least a max, then we say plus plus sums. What is it, 1 to 10, 12, 10? No, it's not correct. Hmm, what's happening? Ah, maybe this should be like this. I mean, just let's make it I, big I, capital I. No, it didn't help. It didn't help at all. Okay, let's look at it in the debug version. Ah, No. Okay, I get it. 1 to 10, 12, 10, 15, 106. Yeah, definitely. A bit slow though. A score of an array is defined as the number of indices such that the sum of this prefix is 0. You're given an array of length n, and we can replace zeros with any numbers. What is the maximum possible score of A that can be obtained by performing a sequence of such operations? So it looks like we have several. So let's look at two zeros. What do we have between these two zeros? We have some sums actually. So this is a sum zero, this is some sum, this is some sum, this is some sum, and we want to find as many equal sums as possible. So again, a very easy problem. So what do we have? N, then we have vi. What do we have then? Okay, ons is hmm. Let's solve this problem with a map. What do we have? And we have some current sum. What do we do? Actually, I think it's long long. No, this is int, but this is long long. So we say s plus equals vi. No, so if vi equals 0, then we have to flush the answer. And we add this q to the answer. And then we say that m.clear s equals 0, and else we do this. After that, we just add 1 times m2s. And now we do the same thing in the end. I think we can just add a 0 to v. Excellent. So 31445, correct. Haha, wrong answer in process 2. Maybe if I have only zeros, then this is not correct. For example, if we have No, it is correct. It says that it is 4, and this is correct. Maybe sometimes I cannot do anything. Ah, the sum is 0. I get it. I get it. Okay, I wasn't correct. So here, if ans equals 0, no, let's do it like this. So if flashes, then we can do it. But else, we just say that Q is M0. Now it dropped a lot. Also I had to make plus plus flashes. Yeah. What is this test? Okay, this is some random test, I don't know. Let's try again. Yeah, let's make a test. For example, what if we have this? Then answer is 10, but what if we do 1 here? And it's only 9. Okay, now it should be 8. But what if we do now minus 3? Then it should be also 8. Yes, it is 8. Now it should be 7. Ah, I forgot to do it in the end, didn't I? So for example here, the answer is 5, but actually it should be 7. Yes, this is a catastrophe. I added a 0 in the end. Did it help? So now it is 7, yes? No? Three, one, four, four, five. Okay, so actually answer is -1 in the beginning. A funny case. So let's consider some interesting case. For example, we want okay. For example, this case we have a 7, but how do we get 7? Yes, because it is 0, 0, 0, 0, 0, then 2, 1, 2, 3, 2. Correct? So it's yes, it should be 7 because I say that this might be -2 and this all jumps by -2. Ah, it should be long, maybe. Maybe it should be long. Okay, it's fine. Maybe somewhere else should be long. Oh, excellent. So I should have made defining long, and this would be fine. But now I'm 220th place. You're given three integers a, b, d. Find any integer. Find any integer x between 0 and 2 to the 60th. A or x is divisible by d, and b or x is also divisible by d. Nice. Okay, first of all, let d be some odd number x times 2 to the power of d. no, not T, S. Then if we have A and it has a 1 somewhere here, or B has a 1 somewhere here, then obviously the answer is false. We cannot make such an X. We cannot make such an what can we make? So this is a number Y. No, number Y is put here. Okay, I mean, so there should be no zeros here. No, not zeros, but no ones here in A and B. Okay, let's assume that A and B do not have ones. In this case, we can divide everything by S, so we can assume that now that D is odd, and A and B are some numbers. What do we know about these numbers? A and B are at most 2 to the 30th. In this case, we do not care about these numbers. We can just put all ones, and the rest is to make some number here such that this is divisible by D. And this is quite easy. AVD will be convenient to use LL. So first of all, let's find the okay. So I take D and count its leading zeros. So if A has some incorrect ones, or B has some incorrect ones, then we say that it is impossible. Okay, else we can assume that D is odd. So we take 2 to the C minus 2 to the O plus 1. What is this number? This number is, no, I don't need to plus 1, just this. Okay, so this is a number. Let's think. So I have this number, and since I have it, I do the following. I need to find such a number f that f times 2 to the 30 plus e is divisible by d. D by something like this. How would I do it? I just find it. So this is difference of O and E modular D. And then I divide it by uh, power mod of 2 to the power of C modular D. And now I shout F to the C or E. It should be fine. Oh, this is not fine. Okay, let's also make some here. And I want to find ans or A percent D and ans or B percent D. Now it is 8. This is not good. Why did it happen? Okay, this is the third. Ah, this is actually the second test case. Why did it happen? So what do we? Ah, D. I'm not interested. Okay. So here I have to use the D, not D. Yes. Okay, and now if I remove it, then everything is fine. Okay. Okay. Problem F or problem E. The position of a left maximum per segment of ray x is the smallest integer I such that. Okay. Find the number of integer arrays B, then let's satisfy the following conditions. What is M? M is just a number. For all pairs of integers, the position of the leftmost maximum on the segment LR of the array B is equal to the position of the leftmost maximum on the segment LR of the array A. Yeah. So, what does it mean? I remember a similar problem. So first of all, there is no difference between A being I mean, if we have several maxima, then we can replace them with any numbers which are decreasing. There's actually no difference. Moreover, if we have some maximum, then these two halves can live in can live separate lives because this is the maximum. So what do we do here? We consider the maximum of this array, and m is at most 10 to the 6. Okay, so we consider so let's consider all maxima in the first array in an understandable order. So first of all, A, then this number, then this number, then this number, then this. I mean, maxima in understandable order. When we do it, when we do it, we have some numbers. So what actually is happening? Actually, for this place, we can choose any number that is at least the previous number. So this doesn't have anything in common with this array, does it? What I want to say is that the answer is the choose number of something over something not depending on the array itself. So we can have any numbers from 1 to n, from 1 to m, and we want to have n numbers. So I guess it's m plus n minus 1 over n minus, choose n minus 1 from m plus n minus 1. So like this. Let's check it. So for example, 3, 3, we have choose from 5. I get it. Sometimes we cannot choose equal numbers. Yes, so when we jump to the left, we cannot choose the same number. When we jump to the left, we cannot choose the same number. And this basically subtracts 1 from our possible choices. So it subtracts 1 from here. So what I mean is when we jump to the left, yes, for example, 3, 2, and now we jumped to the left and took 1. In this case, we cannot. No, it's not correct. It's not that easy. So we had this number, this number, this number, this number, this number, and now we jumped to here, for example. So obviously, this number should be strictly less than this number. No, strictly less than this number, but not than this number. So these two numbers might be equal. No, they cannot be equal. This number should be strictly less than this number. Ah, okay. So I think I get it. So first of all, so this should be 4 over 2, and this is 8. It shouldn't be 8. It's a 6. Why is it 8? No, I think it is m plus n minus 2. So what I want to say is we have basically we want to make a non-increasing sequence of uh, 4 objects, and we want to choose 2 objects. No, 4 objects here. For example, if I choose these ones, this is 3, 3, 3. And for example, this is 2, 3. No, it's 1, 1, 3. No, it's not correct. I need it to be like not like this. Actually, it should be n. I think it should be n. So it should be m plus n minus 1 over n. So I need to choose 3 objects out of these 5 objects. Okay, but when I choose this number, it should be strictly less. It shouldn't be strictly less than this number. Okay, actually, I was wrong. So here, okay, when we jump to the left, so we chose some numbers. Now we jump to the left, for example, somewhere here. So this number, it should be strictly less than this number. Fine. Okay, so what I want to perform is for each position find the number of ways okay, I think I get it. But I should be faster, guys. I should be faster. NM A. So we want to find runs of A. That's it. What I want to say is in this particular case, hmm, I need a segment tree, and I do not want to write it. Maybe we can do it without a segment tree. So I find a maximum in a subarray. Then I solve the problem for these 2 segments. Then I compose the answer. So how do I find a maximum in an array? Fastly. Fast. I don't think there is a way. I'm not sure there is a way. So I find a maximum in an array. Then I solve the problem for two parts. Then I count these prefix sums of the answer. Hmm. Oh man. Oh man. Okay, there is some strange way to do it. There is some strange way to do it. Yeah. But it is really strange. Should I do it? I think yes. So okay. First of all, we need a BVI of positions of length m. And I put all the positions in this array. After that, I say that I need to find array ans for A. Actually, here I can do minus minus A. No, I don't need it. Yes, I need it. I need it. I need to do minus minus A. So I find this strange answer. Oh, this is cringe. This is really cringe. So actually, it's a vector of deck force. So I find array ans and take back element. Great. So how do we do it? First of all, we go from no. We also need to pass two positions. So if L equals R, no, we do not need to return in this case, do we? Okay, I think in this case we just say return vi of 1 and m. No, of m and 1. Now we're assuming that L is not equal to R, so this is a non-empty array. In this case, we can find the maximum. So if pos E is not empty, then x equals pos I dot front and break. No, I cannot do it. It's sad. Now, when we have it, we have a maximum. What if we have a maximum? Now, when we have a maximum, let's divide everything in left part and in the right part. So in the right part, so we need to make a pos 1 and pos 2 for left part and the right part. So, I mean, we need a left hands equals find array ans of a pos 1 l x minus no x m and vi right ans equals find array ans of a pos 1 lxm. No, not lxm, but x plus 1 rm rm equals 2. And in the end, we say that let's put everything in the left hands. How do we do it? Or maybe in the right hands. So, what if we want all numbers to be at most y? So there are two cases. First case is this is y, and then I just multiply it by the number of ways to make it at most y, number of ways to make it strictly less than y. So, first of all, let's assume that x equals 0. I think this is an important case. Then I just find right hands. I say that pos ax dot pop front. Then I find the right hands. And what do I say next? I just say that number of ways with y is just the number of ways where this is at most y. And so I just find the prefix sums. And return right hands. Okay, what do I do in this case? In this case, this is non-empty. So I cannot make it 0 because this cannot be 0 in this case. So I'm saying that right ans 0 is 0 because there is no way that it is 0. Now I iterate over all numbers. So what is the number of ways to make it? To make right ans I, to make the number at most I. First of all, it can be I minus 1. Also, this can be I. What is the modulus? Modulus is 10 to the 9th plus 7. So we do not need this, and we need this. Something modulo MD. What do I put here? I say that I should uh, make this part at most y, at most I, and this is right hand side. But also I need to make the left part at most I minus 1. Modulo MD. And I return right hands. So I just need to fill these pos1 and pos2 things. How do I do it? Okay, let's also, if x equals r minus 1, then we do the same thing, but we pop back from ax. We find left hands like this. Yeah. And x is L, not 0. Then we say that left hands I is actually we don't need the left hands to be at most. No, we need it. What do we actually need? So if we have some array, what do we need in the answer? Here would be 0, and the rest of the things are just going to the right. Yes, exactly. They're just going to the right, and then they sum up. So first of all, I move them to the right. Then left ans 0 is 0, and then I sum them up. Okay, but in this case I cannot do it. So let's make some sort of divide. I don't know how this is in English, but the point is we choose the big part. So if x minus L is greater than r minus x, what do we do? And the left part is greater than the right part. So we just make the new vector pos2 and k. Here we do this, and here we do this. Else we make the same thing, but actually it is pos1, pos1, and pos. So this is if the left part is greater than the right part. So what if the left part is greater than the right part? Why why can't then I go through r minus 1 at I is at least x, and I say that it's greater than x. And I say that pos 2 AI dot push front I, but pos AI dot pop back, yeah. And also I say that for x. And here I do the same thing, but I'm going from left to the right. So pos 1 gets pushback of I, and pos gets pop front. After that, pos AX also gets a pop front. Great. Okay, this failed, but why? Understandable? Not understandable. Right answer 0 is 0. This is a problem. Okay, also understandable. 8, 5. It's actually very correct. Maybe we can just send it and we get accepted. Can you try? Wrong answer. Pretest 3. This is because I needed to make sums here. Here and here. Extraordinary. Now I'm 33rd, and we just need to solve the problem F. We have an array of length n. Initially AI is 2 to the I. A is 0 indexed. You want to reverse this array. You need to reverse this array. And we can replace a number with XOR of this number and the next number. This is an interesting problem. Let's look at, maybe we can look at the examples. So we need a set of operations that reverse the array. Okay, first of all, hmm, so, okay, can we just do it naively? How can we do it naively? So I find the prefix sums, and then I go to the in the opposite direction. No, like this. It will work for other numbers, for example, this one. So I chose this, 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 and this. So this, no, select an integer and replace AI by AI XOR next one. So if I want this one, maybe there is a subroutine that swaps to elements. Maybe there is some subroutine that swaps to elements. Let's look. How can I swap these two elements? I just swap. No. Okay, the problem is I cannot swap in that direction. I cannot swap in that direction. I only can swap it in that direction. So actually I have two elements. First of all, okay, let them be green and red, for example. So first of all, I swap it here. Now it is here. Okay, then I start jumping with these two numbers. I think so. Okay, I have eliminated. I'm not sure how I do it. Okay, what if I just rotate one circle? Hmm. Mathematicians. Okay, for example, let's consider two neighboring numbers. Okay, so what do I have? I have these two numbers and I need to swap them. And also I have some rainbow number. So how, as they say, I can do it 101. So if this is 2, this is 0, and this is 1, I can swap these two numbers, so I get these. Then I swap O and I get. No, it's something strange. Yes, it's something strange because I get this. It cannot be true. Ah, this swaps two elements. So for 3 I need 9. For 3 I need 9. I don't like this method. So I have 3 elements. And I need to swap black and green. Okay, something sensible is to take this black here. Okay, but now we have a problem because this green is not here. Okay, now this one takes. Okay, I can just write the operations. So this is 2. Now this purple takes green and black. And this is 1. Now this is 0, this is 1, this is 2. Now this 0 takes everything from here. Okay, now it is green and purple. And this is 0. Okay, now we clear 1 from this. Oh, we cannot clear. Yes, we can clear. Can we? So the problem is that there are 2 purples now. So if we make this purple, we are okay. But we cannot make it purple unless we can. Yes, we can make it purple. Now we apply the first operation. And this vertex is back to normal. Okay, now we can apply the 0 operation. And this is purely green now. And in the end, we can apply this operation and make this vertex purely black. So we have swapped these two elements. We can always do it. I think we can always do it. Can we always do it? Okay, what if there were 2 elements? Okay, let it be a purple cross. So first of all, we, as always, duplicate. So now it is 1, 2, 3. We duplicate. We want this black point to be here, so we execute this operation. So we applied it to 2. No, I started with 2, so let's again start with 2. First of all, I get a green here. And this is 3. Then I copy it to 2. So I get um, green and black. Then I copy it to 1 and I get all 3. And then I copy it all to 0. And I get black, purple, and purple cross. So my aim is to make this purely 0 and this purely black. Can I do it? The idea was to eliminate rubbish from here. Okay, now I can perform. Okay, I have done all operations with all numbers. What I need to do next is to eliminate okay, the problem that I have is that I want to eliminate both purple and black. And this is quite a problem. This is quite a problem. I don't understand this problem at all. Okay, maybe we can do it in some better way. So, for example, let's assume that we have A0, A1, A2. I mean, it's easier to make with indices. So A0, A1, A2, AL, AN minus first. So we need to exchange A0 and AL and not bother anything else. If we can do it quite fast, then we are okay. What did I try to do? I tried to make some strange sums. So first of all, let's translate AL to A0. Okay, let make some thing for sum. This is like L minus 1 to L. And this is 0 to L. And this is, okay, this is 0 to L. This is 1 to L. This is 2 to L. This is L to L. And this is L plus 1, L plus 2, etc. N minus 1. What do we do next? Now we need to leave only L here. Okay, what we want to do is we want to eliminate all numbers from 1 to L from here. So can we just eliminate L from here? I'm not sure. I'm not sure that it is that easy. Can I just make some progress by rotating this thing? So what happens if we just rotate? We get the following array. So A. It depends on the order. For example, if we start with, okay, let's assume that we start with A0 and go to the, let's start with this number and go to the left. Then we have an minus 1, an minus 2. We have n minus 1, n minus 2, n minus 1, n minus 3, n minus 1, etc. And here we have the sum of all numbers. Okay, what's next? What if we repeat this thing? In this case, we have n minus 1, n minus 2, n minus 3, and n minus 1. Then we have n minus 4 and n minus 2. Okay, something strange is happening. I don't like it. I simply don't like it. No, I don't want to do it. It says that we need to make 200 swaps. So we need to make one swap in 1250 operations. This is a lot. It's really a lot. So maybe I need to continue. Okay, let's think that I need to continue. So what do I do? I made these strange sums. Now I transfer this 0 right to this L. So I continue. So what do I have? I have L, etc. 0L. Then I have n minus 1L, n minus 2L, and here I have L plus 1L. And now when I add it here, I have. So this is actually the sum of all numbers. And here I can get L plus 1, L minus 1. Yeah. And here I have 2L. So now I need to. So there is a 0 here. I want to take the 0 away. Maybe it's somehow possible. Not sure. Maybe in terms of matrices. So I have this matrix, and I want to make this matrix. What can I do? I can add a row to the previous row. Okay, this sounds familiar. I can add a row to the previous row. So first of all, I can make. No. I can make something like this. Then I can Okay, I think I just need to swap two rows and that's it. All I needed to swap is to swap two rows. I don't need to do anything else. So let's choose two rows, for example this one and this one. Oh, I can think that one of them is the first row. It will be easier for me to think it this way. Okay, so let's draw several ones. No, they are too large. 4, 5, 6, 7, 8. And I need to swap this one and the first row. Okay, first of all, we can just do this. And we have a large table here. Okay, now we want to remove these ones because they suck, don't they? Ah, we cannot do it here. We cannot do it with these ones. Okay, if I want to transfer this one there, it seems that I need to continue. Okay, I will continue. I don't want to continue it this way because some crazy things will happen. Okay, maybe I'm not correct. Let's do it another way. So I start with this one, then I start with this one, and then I continue until I get this. Okay, now both of them have ones, and actually I can now, what can I do? I get it. Now you choose this operation. So I have something like this. Then I continue, or do I? No, I do something else. I don't like it. So let's undo this and this and this. So we have something like this. Okay, Now we can apply this row and remove these rows. Then I can spread it to the top and apply this operation. And now no, we have this thing. Okay, we won because we have this row. And now we simply undo everything. So we undo this, and we undo this. And the problem is we would like to undo this, but we cannot for now. Okay, let's wait for it. Now I want to what do I do with this half? I do kind of the same thing. No, I was too fast to do it. Okay, now I apply this row to this row. So I get 1, 1, 1, 1, 1, 1, 1. And then, only then, I can do what I wanted to do. Hmm. Maybe I don't need to solve it manually. Maybe this is easier. Or maybe not. But what can I do? For example, let's start with this matrix. So I can get this matrix. So this one is already all right. Okay, can I diagonalize matrix? So if I have something like this, and there are only zeros here, can I diagonalize it? It should be easy because, for example, let us have some ones here. All I need is to prepare the same ones here. So this is kind of recursive procedure. This is kind of recursive procedure. How is it recursive? So I need exactly. Oh no, it's not recursive. Okay, first of all, I add this row to this row, so this has this one. If it didn't have. Now I have to prepare the exact correct ones here. So what is the asymptotics? I don't know. So t of n is maybe 1 plus preparation of some ones here. Okay, I prepared them. Then I performed the same operation. Now this is purely ones. And now plus t of n minus 1. So what is s of n minus 1? But sadly enough, it seems like this is something terribly big. Okay, how can I prepare some set of ones here? I maybe so it seems like it is always something exponential. Is it something exponential? Okay, let's think about it a little bit. So let's assume that I can diagonalize this matrix. But the problem is that here we have some rubbish. Can I eliminate this rubbish? I don't know. If only I could, for example, I can fix this one, but can I fix this one after that? So if I need to remove this one, I need first to apply this row. I need first to apply this row, always. And maybe it is okay, and maybe it is not. So I need to change it, then change this row, and then again apply it. This seems like something very exponential. I don't understand this problem for real. How can one solve it? Is it even cubic time or quadratic time? No, it seems that this is not a cubic time, this is a quadratic time. So it's like 1.5 squares of n. I don't get it. Maybe I'm too weak in linear algebra, but this is something incredible. We have this cycle of matrices, but it will be some more complicated graph if we have 400 vertices. So I just don't understand how would one how would one do it. Some crazy mathematicians, guys. Some crazy mathematicians. Why is he writing in C without C++? Is he crazy? Who is he? So this is also a mathematician, and this is simply genius. Ah, what? Indonesia? It's funny. How do they solve this problem? Okay, I understand that my place is poor because I was very slow. What about problem F? Why is it so hard? Why is it so hard to comprehend? It can be shown that under the given constraints, the solution always exists. I'm very interested why it exists. I would like to know the proof. So the problem is, so even if there are four elements, I manage to swap them, but something crazy happens after that. I cannot easily swap two elements. This is the problem. The problem is I cannot easily swap two elements. So the guys which solved this problem, they are highly inventive. Or they know linear algebra better than me. Okay, I will chill a bit and then we will continue with the editorial of this round. Okay, let's pass to the editorial of this contest. Okay, the problem A. Problem A. You have n rectangular wooden blocks from 1 to n. Where is my face? Ah, it's right here. Okay, let's just ignore this part of the screen. Uh, let's consider both cases separately. So first of all, 2 divides n. In this case, we have also, let's say that n equals to k. In this case, we have n blocks. K, k, k minus 1, k minus 1, etc. 2 to 1. What is the sum of these numbers? The sum of numbers from 1 to k equals k times k plus 1 half. Sorry. K times k plus 1 halved. So the sum that we have here, it is 2 times this number, but we counted 1 twice, so minus 1. So it is obvious that this is at least k squared. So if we can find an example with exactly k, if we can cover this square with side k, then we win, and we cannot make any bigger because this is strictly less than k squared plus 2k plus 1, which is the next number of square, or the next size of square. And surprisingly enough, you can't do it. You start with k and another 1k, and then you choose two sides with length k minus 1 and 1, then 2 times k minus 2 and 2, etc. When do we stop? We stop when these two numbers get equal. Actually, we don't need to stop where these numbers get equal. So actually, there is even difference in cases of 4 divides n and 4 does not divide n. These are two separate cases. They are different. Surprisingly enough. So, uh, so we have 2 times k, k minus 1 and 1, k minus 2 and 2. And how does it end? It ends with something like uh, let me say something like k halved down and k halved up. So let's assume that these two numbers are different, so they are not equal. In this case, how many lines we have? We have two lines with this tile equal to 0, two places with 1, two lines with 2, etc. So 2 times 1 for 0, 1 for 1, 1 for 2, etc., 1 for k halved. So it's actually k halved plus 1. Yeah, and this is at least k, so this is okay. Yeah. And The second case is when these two numbers are equal. In this case, we cannot put them in different lines. We have to compose one line with them. So actually it will be, no, I wasn't correct. First of all, this should be like this, and this is obviously even greater than k. The second case is when these two numbers are equal, and in this case we get 2 plus 2 plus 2, etc. And these two numbers do not give us two lines, but they give one line. Let me give you an example. For example, k equals 2, n equals 4. Yeah, because in this case, it will be more interesting if I take like 4 and 8. Okay, so I get these two lines, then I get these two lines, and this is enough. It's just enough because I have also I can add 2 times k halved, but this will give me 5 times 4, and I don't need 5 times 4. I only need 4 times 4. So I can compose a square, obviously. And the case when the k is odd is k equals 3, n equals 6. You can always see that it works. It works with with an extra line. So we can actually add one more line with 2 and 1. So if we have an even n, then the answer is k is k. This means it's n halved like this and n halved like this. So what about odd n? What about the case when the n is odd? So n equals 2 times k plus minus 1. Let it be minus 1. It is more comfortable for us. So what can we do there? In this case, let's again find the sum. So we have 2 times 1. No, we don't have 2 times 1. We have k minus 1, k minus 1, k minus 2, k minus 2, etc. 1. Let's sum up these numbers. So we need 1 plus k plus 2 times this sum. And this sum is 2 plus k minus 1 times the number of these numbers. This is k minus 2 halved, but times 2. So this is 1 plus k plus plus 1 times k minus 2. This is equal to 1 plus k plus k squared minus k minus 2. This is equal to k squared minus 1. I don't believe in it. I don't believe it. This is simply a fake. this is not correct. Or maybe it is correct. I got it. Actually, I was wrong here because I have two ones here. So this is actually k squared plus k, not minus 1. I don't need a minus 1 here. And here I also have plus 1. So this is actually plus 1 here, so it's k squared. So again, the question is if I can make a square with side k. And the answer is I can. So I put k here. And now I have this thing. And I need to make k times k minus 1. And this is easy to do. As always, we just compose k minus 1 with 1, k minus 1 with 1, k minus 2 with 2, k minus 2 with 2. And in the end, we either have two tiles which can be composed together, or we have four tiles which can be composed together again. So this is like cases with 3, where we have this tiling, or case with 5, where we have 5. No, I meant, for example, here we have n equals 2 times 3 minus 1, so it is n equals 5. But also, for example, n equals 7. And here we have 4, 3, 1, 3, 1, and 2, 2. So see, in this case, the last row has two different tiles, two different rectangles. And in this case, the last row has two equal rectangles. But nevertheless, anyway, the side is k. So the answer is k again, which is equal to n halved seating. And as you see, always the answer is n halved seating here and here. So we just compose the formula n seating. Problem B. Let's look at the problem B. The problem B is quite straightforward, so I won't explain it much. See, the key idea is that the string of 0, etc. 9 is diverse means that different digits is at least a number of zeros, is at least a number of ones, is at least a number of twos, etc. Okay, let's sum this up. Let's remember that the number of all digits is 9, is 10. So different digits times 10, the number of different digits times 10, is at least the length of the string. And notice that this number of different digits, it is at most 10. Yeah, because we cannot have more than just all different digits. And the number of these digits is 10. So actually this is no more than 10 times 10. That is 100. So the length of the string is 100. So you basically just iterate over all substrings of length at most 100. So you start from every index, start considering all 100 strings, or less if we are stuck in the end of the string earlier. We consider all 100 strings, and in each of them we calculate the number of different digits and the number of each digit. So we can find the maximum occurrence of a digit. We can find the way to do it in the string. And that's how we do it. We just increment the answer after the naive checking of every string. Now we continue with problem C. Zero-sum prefixes. I kind of struggled with this problem because of long, and this is not a sign of professionalism of any kind. But nevertheless, I will explain this problem. So in this problem, you have an array, and for every zero in this array, you can replace it with some number, maybe zero, maybe some other number. And the goal is to get as many zero-sum prefixes as possible. For example, in this test case, let me think. Okay, let's look at something like this. So we can replace all zeros with some other numbers. The key observation is that you cannot change the relative uh, you cannot change the relations between these numbers. What do I mean? Let's naively find all the prefix sums. So we have 1 plus 0 is 0, 1, no, 1 plus 0 is not 0, 1 plus 0 is 1, 1 plus 2 is 3, 2, 4, 2, minus 3, minus 3, 0, minus 2. So what if we change this 0? I want to say that you cannot change the differences between these numbers. For example, what if I replace 0 with 10? Then all these numbers are incremented by 10. This means I cannot do anything with these sums. I can change them relatively to each other. So the best that I can hope for is that the most frequent element among these elements becomes 0. And so I get many zeros. For example, in this case, I don't have any zeros at all in this segment. But what if I can subtract 2 from all these numbers. Then these two 2's become 0, and I have two zeros. And I cannot make any more zeros from this subsegment, just because if I have three zeros, that before adding there were three equal numbers, but there are no three equal numbers in this subsegment. So if I take the most frequent element and it occurs k times, that I cannot have more than k zeros. But actually I can make k zeros just by subtracting this number. So if I replace the 0 with -2, I get +2 numbers, +2 zeros. The same goes for this subarray. Whatever I replace this 0 with, I cannot make more than 1 0 here, because uh, all three numbers here are different. Yeah, so I cannot make more than 1 0. If I have two zeros, then there are two equal elements. And this means that before adding this x, there also were two equal elements, and this is not true. So the solution is as follows. I find all prefix sums. Then I consider all pairs of zeros, of two neighboring zeros, of two consecutive zeros. Then I consider all these prefix sums, find the maximum number of equal sums, and I add them to the answer. The problem is with these sums that are before the first zero. And the problem is I cannot change them. For example, this one, I'd like to change it to 0, but I cannot, because it is always 1. Whatever I make these zeros into, I cannot change this prefix sum. It was 1 and it will be 1, whatever I do. So this doesn't go for this one. And you can see in my submission, yeah, so int flashes is the number of times that I saw a 0. And when I didn't see a 0, I just take m0. So I store all prefix sums in a map. And if I cannot change these prefix sums because there are no zeros, I just take m0 as my answer here. But if I had it, then I take the maximum number of occurrences of a prefix sum, not exactly 0. And it's kind of it. And the thing that I struggled with is this LL and this LL. This LL I already put. I instantly put SLL, but I forgot about this LL. In the problem, you have to use long just because these numbers are big, and the sum of them is also big, and it is bigger. It is even bigger. So it can overflow and ruin your solution. Excellent. Problem D. Constructor. Oh, this was actually an easy one. So what do you have? We have two numbers a and b, and d, and we want to find such x that a or x is divisible by d and b or x is divisible by d. And I said it during the contest, but I will repeat. So if a is not divisible by 2 to some number k, is not divisible, but d is divisible by 2 to the k, then we instantly lose. Because if this is true, so this means that in the binary the binary string corresponding to A, in the last k digits, there is a 1. And this means that if you take or x, there will also be some 1. And this means that it cannot be divisible by d. This is kind of problem. It cannot be divisible by d because d is divisible by 2 to the k. But this string disallows us to be divisible by 2 to the k. So if this or this, then we lost. How to choose the appropriate k? I just took k equals, sorry, k equals uh, built-in CLZ of d, because this function calculates, yeah, it calculates the number of zeros in the end of the binary string corresponding to d. So if it is 6, then it returns 6. No, sorry, not leading but trailing zeros. So it is CTZ. You can Google this function. This is a GNU intrinsic, so it doesn't work on Visual Studio, but I just wrote this function by myself. I had to. So you can see that I actually wrote all these functions for Visual Studio. So they work quite fast in O of 1 time, not in logarithmic time. So, okay. What did I want to say next? Ah, okay, of course. Let me think. Yeah. So since we know it, we can assume that uh, all numbers are divisible by 2 to the k. Let's fix c equals 30. And actually the important thing is that we know that a is less than 2 to the c, b is less than 2 to the c, and d is less than 2 to the c. This is an important part of the statement. Okay, after that, actually we can divide everything by 2 to the k, because we don't need to put ones here. And we need x is less than 2 to the 2c. We do not need any zeros here, any ones here. Actually, let's divide everything by 2 to the c. So now what do we have? We have a is less than 2 to the c minus k, b is less than 2 to the c minus k, d is less, sorry, to the 2 to the c minus k, also d is odd, and we want some x which is less than 2 to the 2c minus k. Okay, what is my solution? First of all, I eliminate all the differences between a and b. And how do I do it? I take the last c minus k bits and I put all ones for x. And notice how a and b are all included into this segment. It's because they are not no more than 2 to the c minus k. So after I choose that x will contain all ones here, this will mean that a or x will equal x, and a and b or x will also equal x. So all I need is that x is equivalent to 2 times c minus k minus 1 modular 2 times c minus k, the first thing, it is equivalent to this number having all ones in the last c minus k positions. And the second thing is that x is divisible by d. This problem can be solved using Chinese remainder theorem because you just have two equivalency relations. So x is equivalent to this number modulo to the c minus k, and x is equivalent to 0 modulo d. I just know how this Chinese remainder theorem is solved. And this is solved in the following way. Suppose that you already know that these are ones. Then you just need to find some number here. Let's it, let's denote it by y. So you need to take x equals y times 2 to the power c minus k plus 2 to the power c minus k minus 1. And this relation holds automatically because this is 0 modular 2 to the power c minus k, and this is what we need. This is what we need. So the left relation holds automatically, and all we need is that this is divisible by d. How can we solve it? So this is equal to 0 modulo d. So y times 2 to the c minus k is equivalent to minus 2 to the c minus k minus 1. And we can divide modular d, yeah, because this number is the power of 2 and this number is odd. So they are relatively prime, and we can divide one by another. So y equals minus 2 to c minus k minus 1 times 2 to the c minus k inversed. And since this is some remainder modulo d, this is from 1 to d minus 1. So this is, as we know, this is less than 2 to the c minus k. Okay? So we can find such y which is less than 2 to the power c minus k. This means that we will find x which is less than 2 to the 2c minus 2k. And obviously it will be less than this number because it is even less than this number. And that's it. So this is found with uh, extended Euclid's algorithm, and you find this product and find the needed remainder y, and then you find x, and you're happy because you can solve this mathematics problem, number theory problem, constructive algorithms problem, bit masks problem, and combinatorics problem. Now, problem E. Problem E. This is crazy. Problem E. I'm a bit lazy to explain problem E, so I won't prove everything. So, first of all, we consider two so the two arrays are similar if for any two segments the left for maximum in this segment is on the same position as the leftmost maximum in this segment. So if they are on the same positions, then we're happy. And what did I find during the contest? I found out that actually, let's consider these two arrays, and let's consider their leftmost maximum. First of all, they need to be on the same position. So this is the leftmost maximum. This is the leftmost maximum. What do we need then? Assume that this number is x. First of all, it means that these numbers are less than x, and these numbers are no more than x. And obviously, these two arrays need to be similar, and these two arrays need to be similar. What I noticed is that this is not only necessary condition, but it is also let's see, how is it said? I forgot the word for this. Sufficient. Of course, this is word sufficient, which I forgot. So this is not only necessary but also sufficient condition. So if you have the equal positions of two leftmost maxima and the left parts of the arrays are similar and the right parts of the arrays are similar, then and also then we win. Okay? So how then the problem is solved? This is solved recursively. First of all, we find the leftmost maximum in this array. This is somewhere. So this is somewhere. Let's create a recursive procedure which finds the following. For array A, its leftmost position and its rightmost position, it finds the array of length m. Okay, let's assume that from 1 to n. And it answers the questions. The question, how many, so qi is how many arrays similar to AL to R such that uh, all elements of array is no more than I. Yeah, such that all elements of this array are no more than I. Okay, so if we write this procedure, then we can run it for the whole array and from L to R, from 1 to n. Thus we get this array Q and we need to output Qm. And I say that we need to make it in this time. If we perform this procedure in O of nm time, then we win. Let's find out how we do it. So I need an auxiliary array. Actually, it will be not in this time, but in logarithmic time. First of all, I need an auxiliary array. This is a vector of vectors, and for each number from 0 to n minus from, okay, let's do it from 1 to n. So it's one indexation. For each number, we store all the positions in A in which the number I occurs. For example, there's A, B, this array, this case, I store and m equals 5. Okay, so I have the vector of vectors, and here I have 0 to 5. Here I have 1 and 4. Here I have 3. And here we have an empty array. So this is an auxiliary array which I pass to this procedure. And with this array, I can find the maximum, the leftmost maximum in O of m time. How do I do it? I just go through the end to the beginning, and I find the first non-empty array. And in this array, I take the first element. This is the leftmost maximum of this array. What do I do next? Uh, so I spent O of m time, and now I know the maximum number in this array. Then I need to run this procedure for these two subarrays. And for this to happen, I need to use my auxiliary array. For this to happen, I need my auxiliary array. And I will explain how I construct it later. For now, let's assume that it is done fast. So t of n gets equal O of m plus t of left part plus t of right part. What do I do next? Then I need to combine these numbers, and this is actually easy. Let's assume that this number is 5. Then I need all these numbers to be less than 4. So if I found the left answer L, is it most 4? Then it is L4. And the right part is times R 5, because all these numbers need to be at most 5. And etc. So the answer is L0 times R1, L1 times R2, L2 times R3, etc. But this is not correct answer, because, as I said, this should be number of arrays in which all elements are at most I. So the maximum is at most I. But in my case, ans I is the number of arrays where maximum is exactly I. For example, ans 5 is how many arrays in which this number is 5. So this is not answer, but it will be an answer if I return prefix sums of ans instead of ans itself. So see, if I consider prefix sums of ans, then along with maximum equals I, there will be maximum equals I minus 1, I minus 2, I minus 3, etc. So all maxima which are less than I or equal to I, they will be in this sum, in this prefix sum. So this is the answer. Okay, the only problem is finding this auxiliary array, because if there weren't such a problem, then it would be O of Mn easily. This is known as master theorem, some advancement of master's theorem. Okay, you can consider a tree of all runs of this function. So for each element of this array, there will be a run of this function, and they form a tree of recursive invocations of this function. So the technique that I use is called I don't know how it is called in English. Sorry. It is called something like, I don't know, recursion with respect to the bigger element. So assume that you have divided this segment into. Sorry, I'm not really used to this. So assume that you have divided this segment into two segments, bigger one and smaller one, and you have some auxiliary array. So let's, in time O of x, so of the smaller one, construct this auxiliary array. And what do we do for this? We just simply remove all these elements from the auxiliary array. For example, we say we see element number I, so we need to remove this element number I. For example, AI equals j. Then we take jth element of this auxiliary array and pop front from it. And to use pop front, if this is actually is not vector of vectors, but this is vector of dex, and you just pop front. And actually, if the x were the bigger one, then you would pop back, not pop front, from this array. So in time O of x, we can make auxiliary array for the whole array to the auxiliary array for this array. I understand this is some sort of heavy light optimization. After that, we can simply construct an auxiliary array for the left part, also in O of n, O of x time, or maybe O of x plus n time. But this isn't important. So in this time, we can construct two auxiliary arrays, one from the initial array and the second one just from scratch. The problem with this approach is that this x is O of n. So actually, we will get also O of n here. So this would be O of n squared. This is not good because n squared can be big. But it is important that we used here the last part x. And here's why. So let's understand this following thing. This O of x is done for each of these elements. So each of these elements got his own O of 1. So there are several elements, and each of them forced us to spend some time on it, some constant time on it. So let's take all elements and look how much time did an element force us to spend. For example, this element. So actually, it forced us to spend some time for every vertex in which it was in the bigger part, in the smaller part. For example, if the right part is bigger, then the left part is smaller, and all elements from this part forced us to spend constant time. Let's call it spend a coin. So each of these elements forces us to spend a coin, and we want to understand how many coins we spent. So naively, every element forced us to spend a coin in each vertex in which it was in the smaller part. Let's simplify it and say that just yes, in the smaller part. But notice that if an element is in the smaller part, then in the next recursive run of the function, the size of array is at least divided. For example, if the size of this array is 16, then the smaller part is at most 7. So if in this vertex the element was in the array of size 16, then in the next vertex it will be in the array of size 7. And actually, each time that this element forces us to spend a coin, the number of elements in the array divides. So the number of coins is logarithmic with respect to n, because each time the element forces us to spend a coin, it also divides the size of the array, and it cannot divide the size of an array more than logarithmic times. So each element bothers us no more than this number of times, and since there are n elements, we have this number of coins that we had to spend. So actually the overall asymptotics is O of mn plus n log n. And this is not very big number. As you know, it is set in the statement of the problem. So that's it. It's some sort of heavy light technique, because in heavy light decomposition you also go down the tree. Every time the size of the tree is halved, you have some sort of light edge. And there cannot be many light edges on any path from the root to the leaf. This was the problem E. What about the problem F? Let's look into the editorial if it is ready. So we want to perform AI equals AI plus AJ for every pair of numbers. Okay, let's assume that I don't know. Okay, this is known. Okay, I'm too lazy to. Okay. So what they say in the editorial is that they want to simultaneously swap several pairs. And how do they do it? For example, n is even. Then we XOR this number with this number. So it is quite known that if you want to swap A and B, you can do it with three XOR operations. First of all, A plus B and B. Then XOR it here, and you get A plus B and A. And then you XOR it back here, and you get B and A. This is well known. Swap. And they say that here you can always do it. So first of all, we want to XOR all these numbers onto this half. Then we want to XOR all these numbers onto this half. And then we want that again to XOR all these numbers onto this half. Okay. So we XOR Okay, first we want to XOR the right half to the left half. First of all, we do these operations from the right to the left. It is understandable. Then we perform an operation for every I from 1 to m minus 1. We undo it, but still this is from 0 to m. Okay, now we are reversing this half, so without bm. This is understandable, and we then we're undoing this half. So we now get this thing. Okay, understandable. So we go from right to the left, from left to the right, but we do not choose this element. So this is done, and everything else is undone. So we have fixed this half, and now we go from the left to the right, undoing all these things. For example, this is from 0 to m, the XOR of all elements from 0 to m. And this is XOR of all elements from 1 to m minus 1. If we apply it here, then we get only 0 and m, but not everything in between. And doing it from left to right, we just get the thing that we needed. Okay, correct. And for odd numbers, it is similar. It is understandable. So, okay, this was kind of interesting problem. I didn't solve it, but it was cool. Nice problem, Igor. ID is by Gil. Then Gil has found a nice problem. Okay. Thank you for watching.